first day of section 11.5, we are going to talk specifically about what is called the determinant. And a determinant is a numerical value specifically calculated for square matrices. And the way the determinant is calculated depends on the size of the matrix. So for a 2 by 2 matrix, the determinant is going to be AD minus BC. So again, A times D minus B times C. And those, what look like absolute value bars in this case, when we're referring to a matrix, is notation for the determinant. And also, it could be written as DET, was the abbreviation for determinant of the matrix. So the difference there is, if it says DET of a matrix, the notation would be either the what look like parentheses or brackets for the matrix, or if entries of a matrix are put in between what look like absolute value bars, that's just asking you to calculate the determinant. So to look at calculating the determinant of a 3 by 3 matrix, we first have to define what are called minors and cofactors of a matrix. So for the determinant of this generic matrix here, A, B, C, D, E, F, G, H, I, the minor of entry A, the way that we are going to think about it is, if I were to cross out all of the entries in the same row as A and the same column as A, the minor of that entry would be the rest of the entries in the matrix. So in this case, the minor of entry A would be E, F, H, I. And similarly, the minor for entry F, I'm going to, in a different color, cross out all the entries in the same row as F and the same column as F, which would leave me the 4 entries A, B, G, H. And again, you can, for any entry in the matrix, you can find its minor just by crossing out the row and column that entry is in, and then the minor would be the rest of the matrix that is not crossed out. And the cofactor for an entry is the same as the minor, except it might differ by a sign. So the way I think about it is, the cofactor could potentially have a different sign as the minor, meaning it could be the opposite sign, positive or negative, depending on the location of the entry. So really the quickest way to find the cofactor would be take -1 and then raise that to the power of the sum of the row and column of the entry. So all that means is consider A in that matrix above. That's in row 1, column 1. So the cofactor of A would be -1 raised to the 1 plus 1, which would be +1, times the minor of that entry. So the cofactor of A and the minor of A would be the same, because the sum of the location, row and column, is an even number. So then for the cofactor of entry F, F is in row 2, column 3, which is 2 plus 3 is 5. So the cofactor of entry F would really be the opposite of the minor of entry F, just based on the location of the entry that we're looking at the cofactor of. And to find any determinant, again for 3 by 3 or larger matrices, you would multiply each entry in a row or column by its cofactor and then add the results. So the idea is we're going to be calculating the determinant, and the way you can think about it is by expanding along a row or by expanding along a column. And it'll make sense a little bit here in a second when we actually compute some determinants for larger matrices. You'll see kind of how that process works out for the cofactors and how we expand the matrix. Before we get into the examples of finding determinants of matrices, we first want to look at a few properties of the determinant, and I'll read them and then kind of explain what that means and how it's going to affect our calculation. So one of the properties of determinants is if each entry in a row or column is multiplied by a constant, then the determinant is also multiplied by that constant. And what that'll allow you to do is simplify a row potentially, maybe factor out a number that all the entries have in common, or scale a row in the matrix by a constant, and you'll kind of see how that plays out here when we start calculating some determinants. You could also take a multiple of one row or column and add it to another, similar to row operations, but you could also kind of perform that operation with columns as well. And one of the reasons is if we can maybe simplify the matrix that we are calculating the determinant of, it'll kind of streamline the computation part of it numerically. So again, you can add a row to another row or a column to another column, and it won't change the value of the determinant. So at times we'll do a little bit of simplifying before we actually, expand a larger matrix to find the determinant. And then the last one is very similar to our row operations, is that if two rows or columns are interchanged, which is obviously allowed in row operations, the only difference here is the determinant will be multiplied by -1. So if I interchange a row or a column, I would just have to multiply my determinant value by a negative every time I do that. So let's actually start computing some determinants for 2x2s. These properties really won't come into play, but they definitely will for 3x3s or larger matrices. So for the first example, we're going to compute a determinant of a 2x2 matrix. So the determinant will be A times D minus B times C. So in this case, A times D is 1 times 1 minus B times C is 0 times 0. So I get 1 minus 0 or 1. For the second example, we also have a 2x2 matrix. The entries are still 1s and 0s, but in a slightly different location. So again, to compute the determinant here, it would be A times D, which in this case would be 0 times 1. And I would subtract B times C, which is 0 times 1. And I would get 0 minus 0 or 0. For the next example, we're going to look at another 2x2 matrix. The entries are obviously not 1s and 0s, so we're still going to follow the same process here. So it would be 5 times 700, which is A times D, minus 7 times 500, which is B times C. So what I get is 3500 minus 3500, which is 0. And it's okay for the determinant of a matrix to be 0. It has a little bit to do with what we're going to talk about next, and inverses of matrices as well. But right now we're just focusing on the computation part of determinants. For number 4, we're going to calculate the determinant. So it'd be 5 times 700 minus 7 times 500, which again in this case would give me 0. Just by moving, interchanging where some of the entries were, we still get a determinant of 0 in this case. Now for the next few examples, we are going to be asked to compute determinants of larger matrices, in this case 3x3. So this is where we'll talk about those properties of determinants, some of those ways we can simplify a matrix before we calculate the determinant, and then also kind of how to expand along a row or along a column to compute the determinant. So here's what that means. So in this case, I look at this first matrix, and if I wanted to compute the determinant, it's a 3x3, so it's going to involve finding cofactors and some of that stuff. But first, I could maybe start simplifying this a little bit. So one of the properties of the determinant is that I could multiply a row by a number, which then multiplies the determinant by that number, which how that's going to play out in this case is if I factored out a 5 from the first row in the matrix, so it would give me 1, 2, 3 on the inside, that would be the same as me multiplying the determinant of that matrix by 5. So that's signified by that 5 being out front, absolute value, what look like absolute value bars of the matrix, 1, 2, 3, 1, 2, 3, negative 9, 11, 7. So I used one of our properties for determinants to kind of simplify that first row. And then I look at my matrix and I see that the first row and the second row are identical. So if I were to subtract row 2 from row 1, it would give me the matrix 0, 0, 0, 1, 2, 3, negative 9, 11, 7. And I know that I can do that because one of the properties says if you add or add 2 rows or 2 columns of a matrix, the determinant doesn't change. So I don't have to put a number out front or do anything with that matrix other than to subtract those 2 rows together. And now at this stage, we're going to look at how to expand or calculate the determinant along a row. And in this case, if you look at the first row, I have 0, 0, 0. So that would be maybe a good place to start, or any row that has more than 1 0, or any column that has more than 1 0 would probably be a good place to look to use to calculate the determinant. Here's how you do that. So the first thing I'll do is I'm going to have 5, and then inside this large set of parentheses is going to be the computation of the determinant. So here's what it's going to look like. I'm going to take 0, which is the entry in row 1, column 1, and multiply that by the minor of that entry. So the minor of that entry would be, or I guess I could call it the cofactor of that entry, because row 1, column 1 is 1 plus 1 is 2, so negative 1 raised to the second power is 1. So really I'm taking 0 and multiplying by the minor of that entry. So the minor of that first entry in row 1 would be 2, 3, 11, 7. And again, that's found from basically, if I were to kind of mentally cross out row 1 and column 1, the 4 entries that are left would be the minor of that entry. And then I'm going to do the same thing along the top row. So then I would have 0, which would be the second entry in row 1, times the minor of that entry, which would be 1, 3, negative 9, 7. Which again, if I cross out row 1, column 2, I get 1, 3, negative 9, 7 are the entries that are left. And then if I do the same thing for the third entry in that row, and I'll talk about the signs here, positive, negative, where those come from here in a second, but the third entry of the first row, the minor of that would be 1, 2, negative 9, 11. So again, how do I figure out the signs here? It has to do with the location of that entry. So again, row 1, column 2 is taking negative 1, raising it to the 1 plus 2, which is negative 1. So that's why it becomes a minus 0 times the minor of that entry, which is that minus 0 is really where the cofactor calculation comes from. And then for the third entry of row 1, it's going to be thought of as, I think of it as negative 1 to the 3 plus 1, because it's row 1, column 3. So negative 1 to the 4th is a positive, which is why there's a plus in between those two terms in this large set of parentheses, times the minor of that third entry of row 1. So then to finish the calculation, what you'll notice is I have a number multiplied out front, and then a 2 by 2 determinant minus 0 times a 2 by 2 determinant plus 0 times a 2 by 2 determinant. So the 2 by 2 determinant would be, for the first one, 2 times 7 minus 11 times 3, and whatever that number is, I'm going to multiply it by 0, and that's going to happen for every 2 by 2 determinant inside the large set of parentheses, which means I'll have a 5 out front multiplied by 0, which would give me a determinant of 0. So the advantage to simplifying this matrix before I calculate the determinant is it makes my calculation actually a lot easier. And you're not always going to get 3 zeros in a row or a column. In this case, we happen to. If I have 1 or 2 zeros, it still will make my computation a little bit easier, which is the advantage of trying to use those properties beforehand to try and calculate a determinant. You don't have to, but it definitely will make your calculation a lot easier, especially if you don't have access to a calculator. For problem 6, we're going to try a similar process. So we're going to take a look at the matrix. It's a 3 by 3 again. We're asked to find the determinant. That's what those absolute value, or what look like absolute value bars signify. So before I try and pick a row or column to kind of expand this and find cofactors, I might look to do some simplifying first. So I look at row 1 and see that they're all divisible by 2. So if I take a 2 out of row 1, I'm going to write that out front, times the determinant of that matrix. Again, that's one of the properties of determinants we can use. And then if I look at row 2 and row 3, I also see that they are all, every entry in row 2 and every entry in row 3 all are divisible by a number. So if I factor out a 3 from the second row and a 2 from the third row, what that gives me here is 2 times 3 times 2 on the outside, which is going to be 12, and then times the determinant of this matrix. And again, the reason why I did that is it makes the calculation a little bit easier. So what I have is 12 times, and then here's where I'm going to pick a row or column to expand along. And I'm going to go across row 1. Doesn't matter. Could be column 1, row 2. You just have to pick a row and column to then calculate cofactors of. And again, the determinant should be the same regardless of where you work. So for this one, I would take 12, which is on the outside, and then I'm going to expand along the first row. So the first entry of row 1 is 4, and that's going to be multiplied by the minor of that entry, which is 3, 1, 4, 3. And again, if I were to, mentally cross out row 1, column 1, the minor would be the entries that are left, 3, 1, 4, 3. And then across the first row, the second entry is 2, and then location of 2 is row 1, column 2, which is 1 plus 2 is 3. So I have a negative 1 raised to the third power times the minor of that entry, which is why there's a minus in between there. So it would be minus 2, which is the entry, second entry in row 1, times the minor of that entry, which would be 1, 1, negative 1, 3. And again, that's me mentally crossing out row 1, column 2, and the other 4 entries are what's left, which make up the minor. And then I'll do the same thing for the third entry of row 1. So plus, because that's row 1, column 3. 3 plus 1 is 4. Negative 1 to the fourth is positive 1. So it's plus 1 times the minor of that entry, which would be 1, 3, negative 1, 4. So now, I don't have all zeros on the inside, so I do have to do a little bit of further calculation, but this expansion of this 3 by 3 matrix, now I have a bunch of 2 by 2 matrices where I can find the determinant of very easily. So what this is going to become is 12 times, and then it's going to be 4 times on the inside, and then the determinant of that first matrix, which would be 3 times 3 minus 4 times 1, which is 9 minus 4. And I'm going to leave it like that for now. And then it's going to be minus 2 times the determinant of that 2 by 2 matrix in there, which is going to be 1 times 3 minus negative 1 times 1, which is going to end up being 3 plus 1. And then it's going to be plus 1 times the determinant of that last 2 by 2 matrix, which would be 4 times 1 minus 3 times negative 1, which becomes 4 plus 3. So if I can carefully compute this, it would give me the determinant of that original matrix. So I'm going to write 12 times, and then 9 minus 4 is 5. 4 times 5 is 20. And then 3 plus 1 is 4, times negative 2 is negative 8. And then 4 plus 3 is 7, times 1 is 7. So 20 minus 8 is 12, plus 7 is 19. So it's going to be 12 times 19, which is 228. So 228 is the determinant of that matrix I was given. And we found that by first simplifying the matrix a little bit, reducing the rows by a constant, or dividing each of the rows by a constant to kind of make the numbers a little bit easier to work with, and then expand it along the first row. And then please be careful with your signs, positive or negative, when you are doing that, and you should get the determinant of, this would be the process to get you the determinant of a 3 by 3 matrix. So we look at the matrix in example 7. It's a 3 by 3 matrix, and we're asked to find the determinant again. But looking at this, what I see is there's a column that is all zeros. So what that allows me to do is, if I were to expand this matrix, and what I mean by expand is compute the determinant by working along that column, it's actually going to make my calculation almost as if you don't have to write anything, especially when you get more comfortable, but I'm going to kind of write it out so you see what happens here. I'm going to expand along that first or that second column without doing any operations. I'm not going to, add any rows together or columns together, interchange anything. I'm just going to write it out from here. So row 1, column 2, that's that 0 there. And then the minor of that would be negative 37, 18, 14, 25. And then row 2, column 2 would be plus 0, because 2 plus 2 is 4. Negative 1 to the fourth is 1. And then that's going to be 0 times the minor of that second entry in row 2. So it would be 23, 47, 14, 25. And then minus 0 times the minor of that third entry in row, second entry in row 3. And then thinking about this, again, I can compute the determinant and then multiply by 0, compute the determinant, multiply by 0. This whole thing is going to become 0. So if you ever see a column or row that's all zeros, you can say that the determinant is going to be 0, especially if you get comfortable with how the minors and cofactors work. But even a row or column that has 2 zeros, I'm still going to look at using that row or column to compute the determinant. It'll make the calculation a lot easier. So because this one had a column of all zeros, or if it had a row of all zeros, writing out the calculation for the determinant should verify that you would get 0 in this case. And then for the last one, I'm going to do a little bit of simplifying first before I compute the determinant. So looking at row 1, all of the entries, one of them 0, are divisible by 16. So if I were to factor 16 out of that first row, I would get 1, 0, negative 4. And then looking at row 3, that's actually everything in there is divisible by 10. So if I multiply that row by 1/10, it's going to, or divide that by 10, it's going to affect the determinant the same way. So seeing how this is simplified, I'm going to try and roll with the first row probably. And the reason I say I'm going to go with the first row is because it has a 0 in it, a 1 and a 0, so it should make the computation a little bit cleaner. Again, you could use the second column, you could use the third row, but again, the third row, second row have non-zero, non-1 entries and some negatives there, so it might be a little more difficult, but you should get the same answer regardless of which row or column you choose. So I have 160 on the outside, and then we'll go along the first row, so I'm going to have 1 times the minor of that entry, which would be 15, negative 12, negative 2, 1. And then determine whether it should be plus or minus. Again, I'm going across the first row, so row 1, entry 2 is, if you add those together, you get 3. Negative 1 to the third is negative, so I should get minus, but it doesn't matter in this case because it's minus 0 times the minor of that entry, which would be negative 8, negative 12, 3, 1. So that whole middle term is going to become 0, but I'm going to write it just so we're in the habit of writing minors and making sure we have the correct sign for whatever entry we're dealing with. And then the third entry, again, it's going to be, after the determinant, it's going to be plus or minus because it's the third entry in row 1. 3 plus 1 is 4. Negative 1 to the fourth is positive, so it's going to be plus negative 4 because the entry is negative 4. And if you want to write that as minus, that's totally fine. I just wanted to explain why it should be plus, and then the negative will come from the entry itself being negative. And then times the minor of that entry, which would be negative 8, 15, 3, negative 2. So if I can then compute the 2 by 2 determinants on the inside and complete the arithmetic there, I should have the correct determinant for the matrix. So what I have is 160 on the outside. Then it's going to be 1 times the determinant of that 2 by 2 matrix, which would be 15 times 1, which is 15, minus 24. And then minus 0 times the determinant of that 2 by 2 on the inside. And then it's going to be minus 4 times the determinant of that last 2 by 2, which would be 16 minus 45. And then that gives me 160 rather. And then 15 minus 24 is negative 9, actually. Oops, forgot the negative there. And then 0 times anything is 0, and then 16 minus 45 is 29. So I have 160 on the outside, and then 4 times 29 minus 9 is 107. So 160 times 107 is 17,120. So the determinant of this matrix for number 8 is 17,120. And that is the process of computing determinants for larger matrices, specifically 3 by 3. So maybe you should simplify first, see if you can, make some of the rows have smaller numbers by factoring out numbers or adding the rows or columns together. As long as you follow those properties and then correctly compute cofactors and minors, you should be able to compute the determinant for larger matrices as well.